ME350 Scaling of Model Results and Modified Reynolds Analogy. A wind tunnel test has been conducted on a scaled model of an airfoil or airplane wing with a chord length of 1 meter. Note that the chord length is the length from the leading to trailing edge of the airfoil. The drag coefficient based on the planform area is measured to be 0.0025 at an air velocity of 180 meters per second for air at 15 degrees Celsius and atmospheric pressure. Note that the planform area is the maximum projected area of the airfoil. These wind tunnel results are to be used to estimate the drag force and power required by electric resistance heating elements within the wings used to prevent ice formation. The actual wing has a chord length of 2 meters, a planform area of 10 square meters, and is moving through the air at an altitude of 6 kilometers, where the temperature is minus 24 degrees Celsius at a pressure of 47.18 kilopascals. For Part A, calculate nominal flight velocity for the actual wing that corresponds to the wind tunnel test conditions. For Part B, calculate total drag on the actual wing for these conditions. For Part C, calculate heat flux needed to maintain a surface temperature of 5 degrees Celsius, which is above freezing. Our first assumption for this problem is that the airfoil is in steady flight with uniform free stream velocity and uniform free stream temperature. This is reasonable if our airfoil is moving at a constant velocity through quiescent or still air. Our second assumption is constant properties for each of our two cases, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our third assumption is that there is negligible radiation for the exterior boundary. This is a reasonable assumption for moderate temperatures combined with significant convection at the exterior boundary. Our fourth assumption is that the model wing and actual wing have geometric and dynamic similarity. For geometric similarity, all of the geometric dimensions, including surface roughness, must be to scale. For dynamic similarity, all of the forces must be to scale. Our fifth assumption is that the air is an ideal gas, which will be used to look up properties. Before we begin this problem, we will look at a table of properties that have been obtained by using the property database in EASE for air as an ideal gas. The conditions for the wind tunnel testing with the model and the actual conditions are presented. Note that at an altitude of 6 kilometers, the temperature and pressure both drop significantly. This results in a drop in density of about 50% and a rise in kinematic viscosity of about 65%. Less significantly, the decrease in thermal conductivity is about 12%, and the increase in Prandtl number is only about 1%. For Part A, to calculate the actual flight velocity, we note that for scaled geometric and dynamic conditions, all the independent dimensionless parameters must match. For the flight of an airfoil, the relevant dependent parameter is the drag coefficient, which is the dimensionless drag force. The drag coefficient is just a function of the Reynolds number for incompressible flows based on the dimensionless form of the governing equations. Recall that the Reynolds number is the ratio of the inertial to viscous forces. Thus, if the Reynolds numbers match between the model and the actual conditions, then the relative magnitude of these forces is also the same. Thus, the conditions are dynamically similar. Using this constraint and substituting in values, we find that due to the changes in properties and dimensions, the scaled actual velocity is 148 meters per second. For Part B, to calculate the total drag on the actual wing, we note that since we have both geometric and dynamic similarity, in particular for this case because the independent Reynolds numbers match, then the dependent drag coefficients must also match. Thus, we can use the results from our wind tunnel testing under significantly different conditions. This is a very powerful tool of engineering, and it is used widely to save a significant amount of time and money. In particular, model testing, for example in a wind tunnel, can be applied to significantly different actual conditions as long as the dimensionless independent parameters match, in this case, just the Reynolds number. Using the definition of the drag coefficient, we solve for the actual drag. Substituting in values, we get a force of 184 newtons. Before moving on to Part C, we will review an equally powerful engineering tool called the Reynolds analogy. We begin by writing the x-momentum and energy equations for a two-dimensional boundary layer flow. We notice that if the Prandtl number is 1 and the pressure gradient is negligible, these equations have the exact same mathematical form. Thus, they must also have the exact same solution. Furthermore, if we look at the dimensionless drag coefficient and the average Nusselt number, we recall that they can be written in terms of the function that is the solution for the velocity and the temperature. Since this must be the same function, we can obtain a simple relationship for the average Nusselt number in terms of the drag coefficient. This result has been made even more general by extending the range of Prandtl numbers for which it can be applied as shown. This result is called the modified Reynolds analogy. For Part C, to calculate the surface heat flux, we can use the modified Reynolds analogy. First, we calculate the Reynolds number. We can use either the actual or model conditions because they should give the same result. Now, we can use the analogy to calculate an average Nusselt number from the drag coefficient of 13,841. From the definition of the average Nusselt number, we calculate an average convection coefficient of 151 watts per meter squared Kelvin. Finally, we use Newton's law of cooling to calculate a heat flux of 4.38 kilowatts per meter squared. Again, note that we are able to calculate a heat flux from wind tunnel testing that did not include any heat transfer measurements, which is indeed a very powerful tool.